spheres and cylinders. So exciting topic, and I think it's a double
joint.
And you're going to start that.
I will just briefly introduce the topic and briefly close it, and Adil will do all the hard work. All of the research you'll be talking about has been joint between us. Been a little difficult at times because he's in Aberystwyth and I'm in Dublin, which geometrically are quite close together, but logistically they could be on different planets. It's extremely difficult to get from one to the other.
There's a river in between.
So it's a wonderful opportunity for us both to be here. Right, what am I going to say? Oh, it says, remember the rattleback. So obviously I've got the wrong side of the sheet paper. Yes. Here we are. We've been talking about rattlebacks. If anybody's interested in rattlebacks, would you give me some more advice on the subject? I'd be very grateful. But I'm here to talk about packing. I'm going to give you just a few remarks of general introduction about this subject, about packing problems. Packing problems usually have to do with hard objects of some kind that you put together. They cannot overlap or deform, and you pack them perhaps into all space, perhaps into a receptacle of some kind, a confined geometry, and then you ask a lot of obvious questions about such packings. That's the subject. And I'm a physicist, so I come to this from physics. Ideas about packing hard spheres, in particular, have always been part of the mainstream of thinking about the solid state, about crystallography, and you probably know the whole story of Kepler and why he got interested through thinking about the snowflake. There are many other examples, and even today in teaching crystallography, hard sphere packings are very useful as a starting point. And then more generally, of course, in soft matter, where I belong, you have spherical colloidal particles, you have granular materials, sometimes idealized as spheres, you have emulsion droplets, and you have foams, and that's where I come from, really, that area. So it's a study of foams that has led me into an interest in hard sphere packings. I'm not going to talk about any of that background, partly because I'm giving a talk tomorrow at 2:15 in TCM over in the Cavendish, which will be aimed at all the physicists. It'll have a little bit of today's material, but a lot of other things beside, and a lot of experiments as well. But if we forget about the physics and we retreat to the mathematics and we content ourselves with the idealized geometrical problem that I've introduced to you, then you still have some choices as to the style of work you want to do. You might be interested in proving something, of course. In proving, for example, that Kepler was right and that the face-centered cubic arrangement of hard spheres is the most dense possible. And you may well know that in recent decades, really, Thomas Hales finally produced a computer proof, as it happens, but a mathematical proof of that hypothesis or that conjecture. Very hard work to do that kind of thing. So that although I know Thomas well and I meet him from time to time, I wouldn't pretend to really understand what he did. It's hard work and it's hard to understand. Much easier is to use the computer to do simulations, exploratory simulations, which of course don't give us any great mathematical, rigorous certainty about the results, but are highly suggestive as to what is right and what is wrong. And today's talk will certainly be in that spirit. It's not terribly difficult to do this kind of exploratory work. And so with the growth of computer facilities, it has become quite fashionable in recent years, and a lot of people are doing it from one angle or another. For instance, there's a whole flurry of papers recently about packing tetrahedra. Tetrahedra, regular tetrahedra, symmetric tetrahedra, do not fill space. So the question then is, what's the best can you do? And I think they've converged to an agreed answer in just the last couple of years, but there have been many stages and alternative proposals for that over recent years. That's just one example. And it struck me in just preparing these few thoughts that it's quite remarkable that we don't have a journal for this subject. When we consider the bizarre outposts of mathematics that have journals now, how strange that no one's thought of this. So if anybody's in the publishing industry, there's a thought for you.
It would be too densely packed.
Yeah, it would be densely packed. It would be, indeed. But that would fulfill a function, I think. There's also no conference, although there wasn't until, 3 weeks ago, we had one in Dublin, which was quite a success, and probably will be the first of an international series every 2 years. That was the consensus at the end of it, that should be so. So it's a growing subject. Mention just a couple of the people who are big figures in it. Torquato at Princeton is extremely productive of the kind of work that I've been talking about. It's not, generally speaking, mathematical proof, but it's all presented in a very mathematically respectable way, if you understand me, the right kind of language. And he's doing a variety of problems in this area, including both ordered and disordered packings. We won't say anything about disordered packings here today, but obviously they raise their own questions of a more statistical character. We will talk about ordered packings today. Someone else who mostly worked on disordered packings, as it happens, is Chaikin from NYU. Chaikin has achieved considerable fame by doing work with M&Ms, those nice little candies that the Americans and ourselves now eat, oblate spheroids, I suppose. And we had the most entertaining talk, didn't we, at our conference from Geoffrey Chaikin. It was tremendous. And one of the many points he made was, if he'd chosen British Smarties instead, it would have been a disaster, because the property of the packing depends in a very interesting way on the axial ratio of the oblate spheroid, and Smarties do not have a good oblate spheroid profile. The ratio's wrong in terms of having a dramatic result. Well, it's a great story and more subtle than you'd think. Okay, well, I'm just checking my little notes, and I think I've touched on all the points I wanted to. Today's presentation will have to do only with hard spheres, no Smarties, and only with hard spheres in cylinders. So we should be able to get through it in a reasonable time. Adil, will you take over?
Thank you.
So these are the various people who are supporting us and coming here and talking to you today. I myself am at Aberystwyth University, but then we have a team of people, including Denis Weaire, and the team is led by Stefan Hutzler there at the moment, and Hawkeye Chan and Aaron Meager have been extremely useful in helping us work along. Okay, so as I say, the title of the talk today is Dense Packing of Spheres and Cylinders, and I'd like to start by giving you a motivation of what I'm trying to work on here. So the question is encapsulated by this first sentence here. What is the best, and by that I mean the densest, okay, packing of hard spheres in a cylinder? That is, given a cylinder of diameter big D, and you have spheres all of diameter little d, what arrangement of those spheres in the cylinder will maximize the packing density? And you can do a sort of a thought experiment, and you can come up with your, just thinking about it, you can come up with the answer for the first few simple packings. So you can imagine that when the diameter of the tube is the same as the diameter of the spheres, it's an obvious thing that they're just going to line up like peas in a pod. Okay? So that we can sort of, we understand straight away. Then you can imagine that, say I increase the diameter of the cylinder slightly, what's the next thing that's going to emerge? And we see that the next thing that emerges is sort of a zigzag arrangement, where each of these spheres, if you look down from above, would be at 180 degrees to the next one. So it's just like a chain, a zigzagging chain going down the column. And you can continue increasing this ratio of the diameter of the cylinder to the diameter of the spheres, and you get more complex shapes emerging. So the next one in the packing is some sort of twisted zigzag arrangement, and you can carry on in this way. Okay? And how have we come to understand what these packings are? What are the best packings for a particular ratio of the diameters? Well, we've done a combination of things. We've done some simulations. I'm not going to go into depth about how we did those simulations, but please ask me afterwards if you want. We've also done some experiments where we drop ball bearings into a tube and see what emerges. And since the group of Hutzler in Dublin are experts in working with foams, we've also done things such as introduce bubbles into microcapillaries and see how they arrange themselves. Okay, and this is a 1.5 millimeter tube here, and you can see a little bubble here, just about perhaps. But I show you they take up some sort of nice ordered packing in the tube. Okay, but I'm going to stick with numerical simulations for the rest of this talk. And what I'm going to say is that what we plot here on the x-axis is the diameter ratio. Okay, so as I'm going towards the right, I'm essentially making the cylinder diameter bigger and bigger. And what I do is I ask myself from the simulations, what's the best packing I found for a particular value of the diameter ratio? And I plot its volume fraction. That is, the amount of space is the ratio of the amount of space occupied by the spheres to the amount of space occupied that's totally available in the cylinder. And what I find when I plot the density of the densest packings I have is that I get a curve that looks like this, and then there's some sort of discontinuity, and then another curve, some sort of discontinuity, and the curve carries on in a piecewise continuous fashion. And these lines here are drawn to illustrate the positions at which these discontinuities occur. And if I examine more closely what kind of structure I have in this regime, for example, you see I get this sort of zigzag structure, which is achiral. And if I increase the diameter ratio past this point, another structure dominates. Another structure becomes the best packing arrangement that I have. And now we see that many of these structures are twisted in some sense. They are chiral. Okay? So over this entire region, I have some sort of chiral structure. There's a narrow band here, which I have another chiral structure. Here at this particular value of d over little d is equal to 2, I get an achiral structure where I just have two spheres sitting next to each other, and then if I go down the next layer, they're just rotated by 90 degrees, and so on and so on. And there's an animation that I always steal from an American scientist, Galen Pickett, which is very nice for illustrating what happens as I increase the ratio, as I increase the diameter of the tube, and it illustrates what happens. It illustrates this best structure I have from moment to moment as I increase the diameter of the tube. So here it goes. The tube diameter is increasing. I jump to another structure, and then I jump to another structure, and then another structure, and so on. Okay? So you can see that as I'm increasing the diameter of the tube, the structure is changing in some sense. The geometry is changing, but the topology is not changing. The number of contacts, the matrix of contacts for each sphere doesn't change. Okay?
These transitions are clean. There's no like bistability overlap or something. If you're actually Well,
During the density, so it really seems to abruptly shift one to the other without.
well, what I see is that there are competing structures in the jungle that I'm not showing you here, and the reason I'm showing you these sort of sudden curves here is because I pick the structure that is now taken over as being the best one. So that's why you see this kind of thing.
Mechanically speaking, there could be for a given ratio.
Yes, you can have metastable structures which, given a shock, might collapse to something denser. Yeah.
So all integer values is a kind of singular.
No, it's just it's just something that you're. It's just a coincidence on this case. That so, for example, I'll show you on the next slide that the next achiral structure, which is a triangle, an equilateral triangle of spheres
Oh,
sitting
I
on top
see.
of the next one, doesn't occur in an integer value.
But how about 4?
Let me jump to the next slide. I think that'll make things a little bit clearer. Okay. So
Could you just
yeah.
yeah, here as well. It decreases at some point.
The density is dropping again, you mean, down here? Yes, yes, yes. I'll explain all of that in a moment. Okay, you see that there are regions where the density is dropping, absolutely. And there are peaks here where you have some sort of best packing structure. There's some sort of local peak in the best packing structures. But that's something I really do want to come on to and talk in some detail about. So the gentleman over there was asking me about these singularities that you see here, 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 and here. These all occur because we're coming up towards some sort of achiral structure, and they correspond essentially to structures which are 2 spheres next to each other on each layer, or 3 spheres, or 4 spheres, and so on. And you can work out precisely where they're located by simple geometry. Okay. Now, what I want to show you about with this graph is that this is an enormous regime of simulations. There's something like, within this region, about 30 or 40 distinct structures that we're looking at. And what we find is that we can split these structures that we see, these various structures we see, into 2 kinds. And this heavy blue line here is there to indicate a division between a simple type of structure and a more complicated type of structure. Towards the left of this heavy line, all the structures are of a type which we call simple packings. That is, all the spheres are in contact with the cylindrical boundary. Okay? But once we go to the right of this line, a new type of packing emerges, which we call multi-layer packings. Multi-layer packings are such that you have spheres which are in contact with the cylindrical boundary, but if you were to take an X-ray through the system, if you were to look inside, you now find spheres which are in contact only with other spheres. Okay? So these are a different type of packing, and we will come back to these right at the end. But what I'm going to do now is I'm going to tell you the story that we set about trying to explore, which is, can we understand this enormous zoo of structures that we find towards the left of this line, these simple types of packings that I have? Okay? Just pause in case anybody wants to ask me anything.
Before one understands it, even the question is how to name them.
Absolutely. Absolutely. Should they?
Could use Welsh.
Okay. So what I want to do is I just want to put up a slide on which I talk about simple packings for a moment. And there are some simple insights that we can take away from the fact that all the spheres touch the bounding cylinder. So here's an example of one of the packings that I'm interested in. And if I look at it from above, you'll notice that that because all the spheres are touching the bounding cylinder, we can make a statement about where all the sphere centers lie. All the sphere centers, therefore, must lie on an inner cylinder of diameter d prime. D prime is different from d. D is the diameter of the bounding cylinder. D prime is the locus of all these sphere centers. And what we can then do is we can say to ourselves, what happens if we take this surface this inner surface, and unroll it onto the plane. Okay, so what I've plotted here is d prime times the azimuthal angle, that is, I'm going around this way, and over here is z, so that is going up and down the cylindrical axis. And what I find is that I can plot the points which correspond here to the sphere centers that I have over here. But now, and more interesting thing is that if I look at the intersection of these spheres with the with the intersecting cylinder, the shapes that you have look more or less disc-like, but they're not exactly disc-like. There's some sort of distorted oval-like shape. And that's an interesting thing that we'll return to in a moment. Okay? But if I concentrate now on looking at the points, just looking at these points on the d prime theta axis and z axis here, if I just look at this for a moment, I notice something else. The packings that I have, if I unroll them onto the plane, come in two types. They are either what I call maximal contact, that is, that each sphere is in contact with 6 other spheres, and these lines here indicate a contact, a neighboring contact. This arrow here is the periodicity vector, so by the time I've gone from here to here, I've actually gone once around the entire cylinder. So I have these kinds of packings, and I've shown you some other examples here, which when I unroll them onto the plane, give me a triangular lattice on the plane with each sphere in contact with 6 nearest neighbors. Those are okay, those are fine. But then more mysteriously than that are what we call line slip structures. So all we did was we unrolled some other structures onto the plane, and what we found was that most of the packing, for most of the spheres, they have 6 nearest neighbors. But there's a region here, like a line going across, where this point here, for example, has contacts with 1, 2, 3, 4 spheres on this side, but with a 5th sphere on the other side, there's a missing sort of contact here. And this defect goes right along, well, goes in a line along the pattern, so it's sort of spiraling up the cylinder. So the question was, okay, we can unroll them and we get these two types of patterns. Can we understand that, please?
The question is that when you do the simulations,
Yeah.
do the simulations introduce a sequence? Do you put them one by one, so you can tell this one is number n and this one is number n plus 1?
Yeah. We did simulations one of two ways. We did sequential deposition, where we would introduce particles one by one. That was we did that on a computer.
Yeah.
We also did simulated annealing, where the particles aren't introduced one by one. They exist as a gas, which is basically we reach a condition where there's a zero overlap between the spheres. Both methods confirmed the same thing, the same structures. Okay. So, as I said, my question at the last slide was, can I understand these structures? And the answer turns out, yes, we can, otherwise we wouldn't be here telling you about it. But in order for me to tell you about it, I have to take a step back and talk about an even simpler problem, which is not packing spheres inside a cylinder, it's packing disks on the surface of a cylinder. You kind of anticipated I was going in this direction. So let me pause now and set up some of the machinery I need to talk about that. So let me talk about disk packing. So we're helped by the idea that, firstly, I know that on a plane, the densest arrangement of disks I can possibly have is to arrange those disks into a triangular lattice. Okay? Now, if I have a triangular arrangement of disks on a plane, what I can then do is I can say to myself, let me just schematize this triangular arrangement, so I just have these points. And what I can do is I can pick any one disk center I wish and choose another disk center and draw what I call a vector. Well, the vector v is a periodicity vector. Draw a vector between these 2 points and then make a cut which is perpendicular to this vector v on both sides. Okay, this then defines a section between the two endpoints of the vector, which I can then excise. I can cut out of a piece of paper and then wrap onto a cylinder of the appropriate diameter. Okay? Now, there are a number of, well, there's a literature about this kind of technique where you wrap a triangular pattern onto a cylinder, and it comes originally from biology, where biologists were concerned with things like arrangement of corn on a cob and so on and things like that, or cells on a pineapple. And for this reason, it's associated with phylotactics, so biologist's word for growing plants and so on. Now, but essentially the idea is very simple. What you do is you take your triangular lattice and you take some starting point and some ending point. And what you say to yourself is that in order to reach this end point from my start point, what I would have to do is I would have to take 5 steps along this triangle here and then 4 steps to go here, or I could have taken 5 steps along here and take 1 step along here. And those numbers I can use to uniquely identify any cut I want to take. So for example, this cut, which I've denoted by these dotted lines here, has numbers 5, 4, 1. Now, of course, these numbers aren't independent of each other. You could have just used the number 5 and 4, for example, to specify those the wrapping entirely. But there are other reasons why we want to maintain this extra index here. But I won't go into that, just as long as you get the general idea of that any wrapping we can assign these indices and identify which wrapping we're talking about. Fine. Now, each time I do that, each time I take such a wrapping, I can, each time I take such a wrapping, and what I'm doing here is just an animation showing you that there's an infinite number of discrete choices I can make for such a wrapping, and each time I'm telling you what the indices are, so 431, 422, 431 again, 440, and so on. What I can do is for each of these wrappings, I can replace these centers you see here with disks, and then wrap it onto the surface of a cylinder, and the packing density, the surface packing density in each case will always be the same. So here are the different choices for the length of the periodicity vector. You can see 1 or 2, √3. So these are all these points here. And then in each case, when I wrap it onto the surface of a cylinder, I get exactly the same triangular pattern. And so they have exactly the same surface density when I wrap onto the surface of a cylinder. Okay? So provided the question you're asking is, if I'm lucky enough to have a cylinder of the right diameter, then you've solved the problem of what's the densest packing of disks on the surface of the cylinder. It corresponds to one of these wrappings. It's done. Okay? So that would be very easy, but in fact, life is not so easy. And the problem we have to ask ourselves in understanding what's the densest packing of disks on the surface of a cylinder is what happens if we're presented with a cylinder which doesn't have one of these special diameters. Okay. So what we did was we said to ourselves, can we see what we can do to break free from this condition that the length of our periodicity vector is fixed to these discrete values? So the first thing we tried was, let's try to shear the lattice. In that way, we'll still maintain most of the contacts that we have, but we can break this condition that the periodicity vector can only have a fixed value. So here I've started off with some particular arrangement with everything with 6 nearest neighbors, but now I globally shear the lattice, and you notice there are broken contacts, and these spheres now have 4 nearest neighbors, but the advantage I now have is I can change the length of the periodicity vector. At any moment I could pause this image and cut along these cut edges and wrap that pattern seamlessly onto the surface of a cylinder, and I'd be able to find something that packs fairly well, packs pretty good onto the surface of a cylinder. Of course, I'm just showing you one particular choice of the direction of the shear I could have done. I could have done the shear instead of along this direction. along any one of the three directions of the triangular lattice. So there are three choices I can make. And what does this do to the density or the surface density of those disks, of the surface packing density? Well, of course, when I start off with the system with 6 nearest neighbors in a structure like 541, okay, I have a maximum possible surface density, but then as I shear the system and I get 4 contacts, the packing density drops, okay, becomes a minimum when I have something with which corresponds exactly to a square lattice. But then as I continue shearing, I'm going to end up in another arrangement where I have 6 nearest neighbors again, and so the density climbs again, and I return to another symmetric packing, which is identifiable by these phyllotactic indices 954. So by taking the structure 541, I can shear the structure and eventually end up at another symmetric packing arrangement 954. Now, that's one thing we could do, but it turns out that this is a red herring in a sense, because we can consider another way of breaking free of this condition that the periodicity vector is fixed. What we tried instead was this. We said to ourselves, let's say we keep most of the structure 6 coordinated, but this time we're only going to break the contacts along a limited part of the lattice. And in a picture or a movie is much better at explaining this. So what I show you is here. We allow one layer of disks to roll over the previous layer of disks. And as you can see, the shear is now confined to this region here. And I start off in some sort of symmetric structure 541. And you can do the count. You can see you go 6 steps along here, 4 steps along here, or 6 along here and 2 along here, and I can end up in another structure 642. And these kinds of shearing deformations localized along a line we'll call line slip. Okay, and what does this do to the density of the system? Well, this time you notice that I start off in some structure 541. This is the previous shearing deformation, but in this case I start off with it 541. I shear now along a single line, breaking contacts only along here. The density again drops, and then as I come back up to this symmetric structure 642, I regain the maximum possible density that I have for packing disks on a plane. But now the important point is that you notice that the relative change in density is much less than when I globally sheared everything, because that shear, the breaking of contacts, is restricted only along a fraction of the system. Okay? So the rest of the story is about these kinds of deformations, and just to illustrate, I can start off with 532, okay, so 5 steps along here, 3 along here, or 5 along here and 2 along here. So these all show 532, but I can make different choices for the direction in which I do the slip, and I can end up in different structures when I do that.
Okay, you say different structures. That's because you've colored some of them yellow.
Yes.
But the structures as a whole globally is the same, isn't it? 633 is the same as 642, for example. They're
Yes.
both just the densest.
Okay, so you can it's not quite true, because when you wrap this thing onto the surface of a cylinder, you can get structures which will be, for example, this one will be chiral because of the orientation of this periodicity vector with respect to the rows here, but this one will be achiral because of the same because of that
On the
point.
plane, they're the same.
They're on the plane, they're the same, but wrapping onto the cylinder, you get something different. That's absolutely
But
right.
the distance between the yellow lines is different. They are different in the plane.
The distances between, yes, that's right, and that counts for the fact that a different fraction of the lattice is being deformed, and therefore there will be a different relative change in the density depending on which line slip I choose to do. So if I show you the next one, here is, for example, the structure 541, and these are all the possible curves I have coming out from it due to these line slips. And you can see the behavior is different, and that's because of the fact that a different relative amount of the lattice is being distorted. Okay? This line here is my previous asymmetric global shear of everything. So that sort of illustrates to you the enormous number of possible potential points of departure I can have from any one symmetric structure to any other symmetric structure. And if I now plot all of them, okay, up to a certain value, the red lines are the asymmetric ones where I globally shear everything, and the black ones are all of my line slips. These points here, these peaks, correspond to my symmetric structures. So, for example, 3, 2, 1 is this arrangement like this, okay? And then I'm connected to 3, 2, 1 by a line slip, and I go to 4, 2, 2, again another symmetric structure, but in between I follow this curve like this, and this just corresponds to this a particular line slip that takes me from 3, 2, 1 to 4, 2, 2, okay? Okay, so I'm almost done now. What has this all got to do with packing spheres in a cylinder? Okay, so what we do now is we go back to this graph I showed you earlier on, where the discs I had weren't discs, they weren't round, they were some sort of distorted oval-like shape. And we say we're not going to deal too much with trying to understand that oval-like shape. What we're going to say is that essentially we simplify the problem by saying that these discs are some sort of ellipsoidal shape. They're stretched more in one direction than another. And we can work out roughly what that stretch factor ought to be due to the curvature of the cylinder within which you're bounding these spheres. And so what we can do is we can start with this sort of disc packing arrangement and stretch the pattern that we have along the direction of the periodicity vector by the appropriate amount. When I say the appropriate amount, there's a lot of thinking that's gone into that, and I can tell you about it after the seminar if you wish, but let's leave it at that for now. I can stretch it by the appropriate amount, and when I do that, all of these curves that I have here transform into this set of curves that I have over here. And there's a set of numbers here which are basically telling you the direction of the line slip. So you remember there are 3 directions for the triangular lattice, let's call them 1, 2, and 3, and these are just numbers corresponding to the direction in which the line slip is happening, 1, 2, or 3. And we can look at the we can highlight out of all of these curves the winning structure, and we can say to ourselves that this is a line slip of type 2, type 3, and so on. And we can compare this to the numerical results that we have, and in those we can unwrap those structures as I showed you earlier on, and ask ourselves what is the direction of the line slip? Is it direction 1, 2, or 3, and so on, and compare directly. So for example, in this region and this region, which corresponds to this segment of curve, we are successful. We've predicted a line slip of type 2. Here again, we're successful of type 2. Here we have, let me pick this one instead, that's better. Here we predict a type 3, but we actually see type 2 for a long time, and then type 3 takes over. And so you'd think, where does this discrepancy come from? Well, actually, it's because of the very simple transformation that we use to account for the curvature of the cylinder. We can show that if we accounted for something more sophisticated, we could take into account these errors, but it would obfuscate the story I'm trying to tell you, which is that up until this point here, we can understand these sphere packings, 80% of them, entirely in terms of simple surface patterns and a simple curvature transformation. Okay? Now, the last thing I have to say before I hand over to Denis is that we then go on to explore structures with much higher, diameter ratios, and we now have another enormous zoo of structures. You can see here that you have a linear chain, you have rings around the chain, but the rings are not flat, they're at an angle to each other, so they're sort of going up like this. You have bizarre sort of shapes encapsulating the spheres. You have spheres which don't touch each other. The internal chain of spheres don't touch each other, but they touch each other, and so on, okay? And if we look at the surface patterns, which you can't see on this projector, because the lines are too weak. They're bizarre surface patterns. They're nothing that we can understand in terms of surface. A full understanding has to come from contacts of the spheres on the surface and the spheres inside. So that's the story up to this point. And now I'm handing over to Denis with a surprise image, and he can talk about this.
Yes, just following on from that last section, those structures don't really follow in any kind of logical sequence like the previous ones did. They're sort of capricious, and you'd have to just recognize them for what they are. And someone asked earlier, perhaps it was Conrad, do you have a problem naming all these things? Well, you saw, I think, that we don't have a problem naming them up to the critical point at which the internal spheres appear for the first time, because they fall into that nice phallotactic story, and you call them LMM, and you line with a line slip 3. I mean, there's a logical way of logic. But when we get these higher structures, you're right, we don't know how to name them. Perhaps after ourselves, Adil, I don't know. But that's one of the things we have to tidy up. I like to say that we're inventing a new subject of columnar crystallography, which someone probably should have done a long time ago. And let's hope it's relevant to something. I'd like indeed to close by mentioning a particular kind of relevance. Anybody who works with these phylotactic structures and thereby is led to stare at pineapples and corn cobs and things of that kind, and to try to read some of the biological literature on that, is amused by it and puzzled by it, perhaps. And we wondered whether these hard sphere packings, the line slip packings, which are new, could have any biological relevance. And after a while I said, well, obviously certainly not, because in biology you don't have the constraint of a given cylinder, and then you have to put things onto it. I mean, that's not, plants don't grow like that, and nor do organs of the human body. So it doesn't look like a biological problem. And then, purely by accident, I think, Adil found this remarkable picture. Just concentrate on the one up on the right, which is the pattern of eggs laid by a certain kind of moth on the branch of a tree. It shows somewhere in the middle a very nice example of a line slip. It also shows further up an example of that kind of homogeneous shear that we tried and dismissed. And the more I look at it, the more I'm puzzled, because, and the more I'd like to see more of these pictures, because I can't imagine quite how the moth does this to achieve such a good packing. You see, if you just started to lay eggs in one place and then made them into a hexagonal structure, kept them close packed, and kept going, eventually you'd end up on the other side of the branch. But in general, you will not have contact between the two growing fronts of eggs. In order to create a line slip structure, the hexagonal pattern has to be at a certain angle. And how would the moth know what angle to orient the hexagonal structure? Now, when we look at more of these things, perhaps that will all turn out to be an illusion, and that is to say, an accident, that this comes out so well.
They are making single layer, right? Or
yes, single layer all the way around. And of course, it's slightly conical, which is complicating things, although it immediately led us to say, right, next month we're doing a cone, and we will. But in the meantime, we'd love to find more of these pictures if we can. So far, we haven't found any of this quality. So with that, thank you very much for your attention.
Well, eating corn on the cob will never be the same again.
Or a pineapple.
Pineapple.
Study
right.
your next pineapple.
Yes.
I used to say that all pineapples are 5, 8, 13 pineapples. But my co-worker, Stefan Hutzler, says, no, he found a different one. You may know that the fascination of that for mathematicians is that the phylotactic numbers are part of a Fibonacci series. 5, 8, 13 are Fibonacci numbers. And there are oodles of papers by mathematicians explaining that. I don't accept any of them. They may well be right, but to me, they're not coherent. Sorry.
Well, same kind of structure can be found for making carbon nanotubes.
Yes, precisely.
So, from graphene
Precisely.
to make a cylinder, and exactly the same argument.
With the same notation. The carbon nanotube, if it's an ordinary nanotube, that is to say of constant diameter, is just one of the perfect phylotactic structures that we have been talking about. The question of these line slips doesn't arise in that case. Of course, some nanotubes might change their diameter and they look a bit like this, and you find another point of contact. Furthermore, if you make big enough nanotubes, you can start putting atoms in them, and you begin to see some of these structures that we're talking about. I don't think there's a big literature of that, but that's another possibility for applications of the kind of packing results that we have.
The nanotubes, maybe, has anyone filmed the moth laying eggs?
No, this is only recently that we became aware of this. And in fact, I've been saying to Adi, there are experts on every conceivable subject in Cambridge. So we must find the person who knows all about Saturnidii.
An expert on mothballs.
Or the Museum of Natural History in London is off somewhere.
Yes.
Most of those pictures have been found by scouring the internet, and they're just taken by hobbyists. And
Yes,
so
these moths are kept as pets. People breed them. So that's where the photographs have come from, I think.
Well, you have to visit the zoology department in the Botanic Gardens.
Yes.
While you're here.
This is just and conformal differential and hyperbolic geometry, there's something called an earthquake, which is the exact, it's not, you have kind of a flat structure, but it's the same thing. You take a line in a surface, or an infinite line, and you slip along it. It's called earthquake for obvious reasons. And then this gives you a path of metrics on the surface. So that's quite useful in optimizing, finding the best metric. And so instead of trying to continuously deform it, it's far more efficient to slip.
That's very interesting.
But it's called an earthquake, which seems
one could take these structures and do a stereographic projection onto a plane and see if that looks interesting.
right. So this, you have to use the hyperbolic, you have to use the Poincare disk, but in which case it's just an arc like that, you slip along. But it's the same principle. It's cultural comment.
But neither the moth nor, I suppose, nor the nanotubes, they're not made by wrapping a sheet, which is where the problem comes. The problem is that you would like to wrap a sheet and the two edges don't make contact, but this probably grows in an axial direction rather than in azimuthal direction.
Yes, it's not wrapped except in a mathematical sense.
Yeah.
But the diameter is fixed here. That's the problem the moth has. It can start to make its perfect hexagonal, but it's going to meet at the other side. The question is what happens at the other side. The moth sits and scratches its head and makes some decisions at that point, and I would love to see a movie of that.
This is a problem. It's like the other side of the moon. You see, we can't see the
Yeah,
other side.
exactly.
The question really is, how does it decide what choices it makes step moment to moment, where to lay the next egg? So it might be that it goes around the cylinder, or it might be that it builds something
With
in
a
the
single
patch.
line, you mean? With a single line, Ron?
Yeah.
I think that's most unlikely.
Okay.
That's a very mathematical
This
model.
would be my intuition. That it goes in a single line.
No.
Yeah.
No.
But it could
Could it
happen.
be that
Well,
it
we
lays down
take a
some
bet.
fluid that drives and then
We-
the dynamics kind of force it into one of your packings?
I really don't know because I've never. We have zero literature on.
I think
this.
it's
We-
just careful placement in a hexagonal pattern, and
we,
eventually
we
it joins
just
on the
need
other
one
side.
one
I'll
person
bet
with a good
beers on
video. One person with a good video movie of
I think
one of
that's
these
a good
patterns
theory,
it would
that
be.
puts down a paste, and then actually there's a dynamical process that maximizes it in the process. So
He's
Doesn't
not
have to think, runs
so
automatically.
convinced.
good idea.
I were the moth.
If you were the force of evolution 3 billion years ago, you would have decided on that.
It would take ages to find the right twig.
That's what they do. They look for the right twig.
Of course, the question then is why does it do it? What's the advantage of wrapping so densely?
People warm. What climates has it done? Who knows?
But it's also, I think, for sort of preventing attack from predators.
This,
Much,
this
much harder to pick them off if they're densely
exactly.
packed.
This is exactly
So
what
that's more the reason.
we have a friend in the Butterfly House. This is a public museum you can go and visit near Aberystwyth. And when I asked him, he said exactly this thing. It's probably harder for a predator to pluck off because you can only pluck off on the edges then of the pattern.
And I bet there are pictures of them being laid. I'm trying to think if there's any David Attenborough films that they have. I mean, there must be.
But some of them make disordered patterns as well. So we have to be careful to get the right species.
Let's write to David Attenborough.
That's
Exactly.
There must be some advantages in having an FRS, yes?
Yeah, right. Zero man. Yeah.
We should have him over here.
I just one question about the average of the contact number.
Yeah.
So if the ratio goes to infinity, so how to behave the average of kissing contact number? It's convergence to the 11. So as
So what we expect, I think you're talking about
yes, yes.
this graph, not this one, next one. This graph here, as I go towards infinity along here. So,
Average so go to the 12.
so what we're doing is essentially we're making the cylinder diameter bigger and bigger and bigger and asking ourselves what's the densest packing inside there. Now in the limit that you go towards infinity, the influence of the boundary becomes negligible. And therefore you expect to recover a FCC lattice. That would be my intuition.
How many contacts, that's your question,
Yeah.
for each sphere? How many contacts does it make in that limit?
In the FCC limit,
12 contacts.
It is 12. It's
12
it's the same as
contacts.
dodecahedral.
Forming sphere, or
Mm.
6 per sphere.
so the density of the FCC lattice
You can fill
is...
space with what? With dodecahedra, is it, or icosahedra?
You can't fill space with icosahedra.
What's the
Can you
center
do
of the
it with
lattice?
dodecahedra?
No, cubes.
Only cubes.
No, cubes.
No, icosahedra you can.
You can?
The FCC gives an icosahedra. Yes.
Okay.
That's the question.
So icosahedra, so count the edges.
And one more, so about this not smooth point, so it's increase or so decrease so if go to infinity, so it's increased to this continuous time is so getting shorter and shorter or so longer.
You mean the distance between the peaks? Does it get smaller and
Yeah.
smaller?
Yeah.
Is that what you're asking?
Yes.
Okay. Well, I can't say anything beyond this line over here because I don't know where the peaks are coming. You know, I have no way, analytical way of... Well,
There is a regime there that we haven't explored, which we could have done, and that is to say, we will continue to go to the right, but with the condition that the spheres all contact the cylinder.
Yes.
The
Yes.
slightly, not entirely artificial
Yes.
condition, because they could be on the cylinder just as well as when the butterfly is laying its
Yes.
eggs.
Yes.
Well, we just chose not to do that. We chose to stick with the original problem, and then the problem changes where the dashed line occurs,
So in the
and becomes very difficult.
Yes. We can continue the problem of just packing on the surface of the cylinder as far as computer power allows,
The analytics is all worked out. You're just confirming everything with the computer is the only difference.
Yes, we could just do the whole thing
Yeah,
analytically.
yeah. Yeah. In fact, as we go to larger and larger cylinder diameters, the effect of that curvature transformation, the higher order effects that we neglected, become negligible. And then our transformation becomes exact, more, I mean, within error. And then we can really, with authority, say we can predict these packings.
So probably even from that point on,
Yeah.
pretty reliable
Yeah.
to do it analytically.
So
Something we should do.
the non-smooth point so might be finite or infinity, or maybe so if go to infinity, so maybe so not non-smooth point maybe so greater than so not appear don't appear the just I thought discontinuity point it might be finite.
Okay.
Yeah, I'm not sure, but I'd like to ask you to finite or infinite or.
Sorry.
But look, Adil will be here until Friday, and I am as well. So why don't we have a session? Yeah?
Sure.
We'll have our own private session.
Yeah.
Conrad.
Just one comment. There is very important practical situation. Unfortunately, not with spheres, more with cylinders. It's fixed bed reactors.
Yes.
Processing wood pellets, which
Great.
are very well-defined
Yeah.
cylinders,
Yeah.
all the same
Yeah.
actually. And the density of packing of that, it's tremendously important in
I've
practice.
seen a-
Very similarly, catalysts that are made as pellets.
Yes.
It's a question, what's the best shape?
Yes.
I'd love to ask you a little bit more about that later because that's useful. But there is a paper I've seen where they're packing small cylinders inside a cylinder as well, and then they shake it essentially.
Exactly.
And they get, the dense packings have this pneumatic order going up all the cylinders line up essentially. Yeah.
Hard to achieve that. by
But
shape.
it never happens in practice. Yeah.
Okay. Okay.
Yeah. I think perhaps we stop there. Time for lunch. And thank Dennis and Adil for a very exciting and interesting seminar.